To today's video on stoichiometry. Stoichiometry, as we know, is derived from the Greek words stoichion, meaning element, and metron, meaning to measure. And that's what we've been talking about in class, is how can we measure relationships between different substances in a reaction. And so in more descriptive language, it's the study of quantitative, which just has to do with amounts, relationships between substances in a chemical reaction. And those amounts can be moles or grams or liters. Grams or liters are much more useful to us to actually measure in the lab because I can put things onto a balance and it'll read out a mass in grams, or I can measure a certain volume in liters. Moles aren't directly measured in that way. So why is stoichiometry useful? In the examples that we're going to look at here, for example, in the reaction A plus B yields C, you may want to know how much of C could be produced from a given amount of A. You might want to know how much B you would need to produce a certain amount of C. Or you might want to know how much A you need to completely react with an amount of B, or any other combination of things you might want to know from that reaction. But that's why stoichiometry is going to be useful to us. And it's important to remember here that when we talk about how much, we're talking about an amount, typically in grams or moles or liters. My conversion factors I'm still going to be using here look the same as what we have been using before. So I have molar mass in grams. I have Avogadro's number of particles in 1 mole. I have a new conversion there on the right. This conversion here, 22.4 liters, we're going to start using this a little more. This is for when I have gases and I want to know how much space those gases occupy. So more on this later, but this is another conversion that we could use. And of course, these conversion factors can be flipped when I need a different unit to cancel. So, stoichiometry all starts with a balanced chemical equation. You cannot do any stoichiometry until you have a balanced chemical reaction. When you have that, you can compare any two substances in an equation. It does not have to be only reactants to products. It can be reactant to reactant, it can be product to product. Any useful combination of two substances. This is important because in a chemical equation, substances are going to react in a specific and constant ratio. This allows us to build mole-to-mole ratios, which are written as conversion factors. As long as I know the amount of one substance in a reaction, I can determine the amount of anything else in the reaction. So let's think about a reaction on the big scale. If I have this reaction, 3 molecules of hydrogen reacts with 1 molecule of nitrogen to form 2 molecules of ammonia. This is what I've been having you draw pictures of in class, and what the picture here on the screen is showing you. I can think about this in terms of molecules, but we want to think about this reaction on a macro scale, something we can see and measure in front of us. Lots of molecules need to react, not only a few at a time. So if I think about the reaction in terms of groups of atoms, like a mole, then the ratio stays constant. So I have 3 moles of hydrogen molecules reacting with 1 mole of nitrogen molecules to form 2 moles of ammonia molecules. When I put the word mole in there, this is going to be much more useful to us in the lab. This is going to allow me those lots of molecules I need for the reaction. What this is getting me to is the idea of a mole ratio. And so I have 2 examples of mole ratios written on the screen. This is one relationship. So 2 moles of ammonia is produced when 3 moles of hydrogen reacts. That's a relationship given to me by this equation. I can write that relationship 2 different ways based on which unit I need to cancel. And so these aren't different conversions necessarily. They're the same relationship, just written different ways based on what unit needs to cancel. I can get any other number of relationships or ratios from this equation also. I just picked two substances from this equation to show you. It's important that when you write these conversion factors, you want the coefficient and the unit and the formula to be as clear as possible. And you'll see why when we do some examples. Okay, here is our mole island diagram. You will have a handout of this, so don't feel like you need to copy this down, but this is in your notes and I'll give you a bigger copy as well. But what this is showing you, the main part of this diagram is this step here, getting from moles of one substance to moles of another substance. That is the new part of stoichiometry. And this, how you get there from moles of a known substance to moles of something else, is through the coefficients of your balanced equation. Okay, so you can pause the video and take a minute to study this map. Again, it's also in front of you, but we're going to be using this quite a bit. So here's our plan for when we set up these problems. We, again, always need to start with a balanced chemical equation. If it's not balanced, balance it. Sometimes you might have the words in a word equation and you need to write the formulas for it, and if that's the case, then think really hard about how to make those formulas and then balance the equation. Then I'm going to write down the given amounts under each chemical. Typically I'm only going to be given one given amount in the problem, but it might depend on what other type of problem it is. But write it underneath the chemical. And then we're going to put a question mark and a unit by the chemical you are solving for, and that's the unknown. Then I'm going to follow the stoichiometry path to determine which steps I need to do and which conversion factors I need to do to solve my problem. And I will show you a few of those examples in part 2 of our video. So you can pause, rewind, get anything else you need to from the notes, and we will see you back here for part 2 when we look at examples of stoichiometry. Recorded.